In September 1931, a racing seaplane roared over the Solent at speeds no aircraft had ever achieved, shattering records and silencing critics who believed the future of aviation belonged to slow, sturdy biplanes. The British public watched in awe as Reginald Mitchell's Supermarine S6B completed 7 perfect laps at over 340 miles per hour, winning the Schneider Trophy permanently for Britain. Days later, the same aircraft broke 400 miles per hour, a barrier many experts had declared impossible for heavier-than-air machines. Yet the Air Ministry and senior officers in the Royal Air Force remained skeptical. Racing planes were toys, they argued, impractical for real military work. Mitchell knew better. The lessons learned from pushing seaplanes to their absolute limits would soon save a nation. Reginald Joseph Mitchell was born on May 20, 1895, in Taka, a small village near Stoke-on-Trent, in the industrial heart of England's Potteries region. His parents were teachers, and his father later ran a printing business. From childhood, Mitchell showed a natural aptitude for mathematics and engineering, spending hours sketching mechanical designs and studying the principles of motion and force. In 1911, at age 16, he was apprenticed to Kerr, Stewart and Company, a locomotive engineering firm in Stoke-on-Trent, where he learned the fundamentals of metalwork, stress analysis, and precision manufacturing. He attended night school to study advanced mathematics and mechanical engineering, often staying long after classes ended to work through problems that fascinated him. In 1917, at age 22, Mitchell made a bold decision that would change his life. He left the secure world of locomotive engineering and moved to Southampton to join Supermarine Aviation Works, a small company specializing in flying boats and experimental aircraft. The move was risky. Aviation was still a young industry, financially unstable and dependent on government contracts that could vanish overnight. But Mitchell saw opportunity. Aircraft design was evolving rapidly, and he believed that speed and efficiency, not size and strength, would define the future of flight. Within 3 years, Supermarine recognized his talent and appointed him chief engineer. By 1927, he was technical director, responsible for every aircraft the company designed. Mitchell's early work focused on flying boats, large aircraft designed to land on water, used primarily for maritime patrol and passenger transport. These were practical machines, but they didn't capture Mitchell's imagination. He was obsessed with speed. In 1919, French industrialist Jacques Schneider had established a trophy for seaplane racing, offering a prize to the nation whose aircraft could achieve the fastest speed over a triangular course. The competition was held biennially, and by the mid-1920s, it had become the most prestigious event in aviation. Nations poured resources into building faster, more advanced aircraft, pushing the boundaries of aerodynamics and engine design. Mitchell convinced Supermarine's management to enter the competition. In 1925, Mitchell designed the Supermarine S4, his first entry in the Schneider Trophy. The aircraft was revolutionary, featuring a sleek monoplane design with cantilever wings, eliminating the external bracing wires that created drag on traditional biplanes. The S4 was fast, reaching speeds over 220 miles per hour in testing, but during the competition it crashed due to flutter in the wings, a phenomenon Mitchell hadn't fully understood. The failure was devastating, but Mitchell learned from it. He studied the problem obsessively, consulting with aerodynamicists and conducting wind tunnel tests. By 1927, he had designed the S5, incorporating mass balance control surfaces to prevent flutter. The S5 won the Schneider Trophy, validating Mitchell's approach. Mitchell continued refining his designs. In 1929, the Supermarine S6 won the Schneider Trophy again, achieving speeds over 328 miles per hour. The aircraft was powered by a Rolls-Royce R engine, a specially designed power plant producing over 1,800 horsepower, more than any engine then in existence. Mitchell worked closely with Rolls-Royce engineers, learning how engine power and airframe design had to be integrated from the beginning. The S6's fuselage was streamlined to reduce drag, its wings thin and aerodynamically efficient, and its cooling system used surface radiators built into the wings to dissipate heat without adding bulky external components. Every detail was measured and optimized. By 1931, Mitchell was ready for the final Schneider Trophy competition. The S6B, an improved version of his earlier design, featured increased fuel capacity, refined aerodynamics, and an uprated Rolls-Royce R engine, producing 2,300 horsepower. The British government, facing economic pressure from the Great Depression, initially refused to fund the effort. Private donations, including a substantial sum from Lady Houston, a wealthy philanthropist, allowed Supermarine to compete. On September 13, 1931, Flight Lieutenant John Boothman flew the S6B over the Solent, completing the course at an average speed of 340 miles per hour. Days later, Flight Lieutenant George Stainforth pushed the same aircraft to 407 miles per hour, setting a new world speed record. Britain had won the trophy permanently. The establishment dismissed the achievement as a spectacle. Senior officers in the Air Ministry argued that racing seaplanes had no military value. Fighters, they insisted, needed to be stable gun platforms, easy to fly, and capable of carrying heavy armament. Biplanes, with their robust construction and proven reliability, remained the standard. The Hawker Fury, a biplane fighter introduced in 1931, was considered state-of-the-art, capable of reaching 207 miles per hour. Few imagined that a monoplane racer, stripped of floats and adapted for land, could serve as a practical fighter. Mitchell disagreed. He had learned that speed and maneuverability were inseparable, that reducing drag improved every aspect of performance, and that advanced aerodynamics could produce aircraft far superior to anything then in service. In 1933, the Air Ministry issued Specification F-730, calling for a new fighter to replace the Bristol Bulldog biplane. The requirements were conservative: 4 machine guns, a top speed of at least 195 miles per hour, and the ability to land at low speeds for operations from small airfields. Most manufacturers submitted biplane designs. Mitchell proposed a monoplane, the Supermarine Type 224, but it was compromised from the start. The Air Ministry insisted on an open cockpit, fixed landing gear, and the Rolls-Royce Goshawk engine, an unreliable design that overheated constantly. The Type 224 was slow, underpowered, and failed to impress. Mitchell knew he had delivered a mediocre design, and it frustrated him deeply. Mitchell's frustration coincided with personal tragedy. In 1933, he was diagnosed with rectal cancer, a disease that would eventually kill him. He underwent surgery, and doctors managed to remove the tumor, but they gave no guarantees. Mitchell was 38 years old, at the peak of his creative powers, and faced with the possibility that he had only a few years left. Rather than retreat, he doubled his efforts. He convinced Supermarine's chairman, Sir Robert McLean, to fund a private venture, a new fighter design that would ignore the Air Ministry's conservative specifications and pursue performance above all else. Mitchell called it the Type 300. It would become the Spitfire. Mitchell applied everything he had learned from racing seaplanes. The Type 300 would be a monoplane with retractable landing gear to reduce drag, powered by the new Rolls-Royce Merlin engine, a direct descendant of the R engine that had powered his Schneider racers. The fuselage would be narrow and streamlined, the cockpit enclosed to reduce drag, and the wings thin and aerodynamically efficient. But the wings posed a challenge. They had to be thin enough to minimize drag, yet strong enough to house the landing gear, fuel tanks, and armament. Mitchell and his team, including aerodynamicist Beverly Shenstone, decided on an elliptical wing shape, the most efficient planform for minimizing induced drag. The elliptical wing became the Spitfire's signature feature, but it was not copied from other designs. Some critics later claimed Mitchell had borrowed the shape from the Heinkel HIA-70, a German transport that first flew in 1932, but Shenstone dismissed the accusation. The Spitfire's wing was thinner, with a different cross-section, designed specifically for high-speed flight and structural efficiency. The ellipse allowed Mitchell to vary the wing thickness along its span, keeping it thin at the tips for reduced drag, while making it thicker at the root to accommodate the landing gear and weapons. The shape also distributed stress evenly, allowing a lighter structure. It was elegant engineering, driven by physics, not aesthetics. By 1936, the prototype was ready. On March 5, 1936, test pilot Joseph "Mutt" Summers took the Spitfire into the air for the first time at Eastleigh Aerodrome near Southampton. The flight lasted 8 minutes. After landing, Summers reportedly told Mitchell, "I don't want anything touched." It was the highest compliment a test pilot could give. The Spitfire handled beautifully, responding instantly to control inputs, and its speed exceeded expectations. The Air Ministry, impressed by the performance, placed an initial order for 310 aircraft in June 1936. Mitchell had proven that a monoplane could outperform any biplane in service. Mitchell continued refining the design, but his health was failing. The cancer had returned, spreading through his body. He underwent further surgery in early 1937, but the disease was beyond treatment. Mitchell spent his final months in pain, yet he insisted on overseeing the Spitfire's development. He was often seen at Eastleigh, sitting in his yellow Rolls-Royce at the edge of the airfield watching test flights. On June 11, 1937, Reginald Joseph Mitchell died at age 42. He never saw his aircraft in combat, never witnessed the Battle of Britain, and never knew that his creation would become one of the most famous fighters in history. After Mitchell's death, his successor, Joseph Smith, continued developing the Spitfire, introducing improvements and variants that would keep the aircraft competitive throughout the war. By the time World War II began in September 1939, 9 RAF squadrons were equipped with Spitfires. During the Battle of Britain in 1940, Spitfires became symbols of resistance. While Hawker Hurricanes, more numerous and rugged, bore the brunt of the fighting, Spitfires engaged the Luftwaffe's Messerschmitt Bf-109 fighters, proving themselves equal or superior in maneuverability and speed. Spitfire pilots shot down 529 enemy aircraft during the battle, cementing the aircraft's reputation. The Spitfire's success vindicated Mitchell's approach. He had believed that reducing drag was the key to superior performance, and the Spitfire proved it. The aircraft's thin, elliptical wings, streamlined fuselage, and retractable landing gear minimized drag, allowing it to achieve speeds over 360 miles per hour with the early Merlin engine. As more powerful engines became available, the Spitfire's performance improved. By 1944, later variants reached speeds over 450 miles per hour, faster than almost any piston engine fighter. 24 major variants were produced, each incorporating refinements, but the basic design remained Mitchell's. Mitchell's legacy extended beyond the Spitfire. His work on the Schneider trophy racers had demonstrated that high-speed flight required meticulous attention to aerodynamics, structural efficiency, and engine integration. Those lessons influenced aircraft design worldwide. The North American P-51 Mustang, one of the best American fighters of the war, featured a laminar flow wing inspired by similar aerodynamic research. The Italian Machi C-202 Folgore incorporated streamlined design principles pioneered by Schneider racers. Mitchell had shown that speed was not achieved through brute force, but through eliminating inefficiency. Mitchell never sought fame. He was a private man, uncomfortable with publicity, who preferred the drafting table to the podium. While his Schneider racers were celebrated, Mitchell remained in the background, focused on solving technical problems. He rarely gave interviews and avoided the spotlight. His colleagues remembered him as meticulous, demanding, and utterly dedicated to his work. He would spend hours calculating stress loads, testing scale models in wind tunnels, and consulting with engineers. He believed that great aircraft emerge from disciplined analysis, not flashes of inspiration. Every line on his drawings had a reason, every component a function. The Spitfire became a cultural icon, but Mitchell's contribution was often overshadowed by the pilots who flew it. After the war, historians began recognizing Mitchell's genius, understanding that the Spitfire's success was rooted in his relentless pursuit of aerodynamic perfection. He had transformed the lessons learned from racing seaplanes into a fighter that could outperform anything the enemy fielded. The skeptics who dismissed his racers as impractical had been proven wrong. Speed, it turned out, was the most practical quality an aircraft could have. Mitchell's story is a reminder that innovation often meets resistance. The establishment clings to what works, even when evidence suggests something better. Biplanes were reliable, proven, and understood. Monoplanes were risky, experimental, and unproven. Mitchell's willingness to challenge convention, to apply rigorous analysis to every problem, and to trust his calculations even when others doubted, ultimately saved Britain. The Spitfire gave the RAF an edge in the Battle of Britain, a narrow margin that made the difference between victory and defeat. When Mitchell died in 1937, obituaries praised his achievements, but few understood the full scope of his contribution. The Spitfire was still unproven, a new design with only a handful delivered to the RAF. It would take years of combat to reveal its true capabilities. By then, Mitchell was gone, his legacy carried forward by pilots who flew his aircraft into battle, engineers who refined his designs, and a nation that owed its survival to a man who believed that speed and efficiency mattered more than tradition and caution. The Schneider's trophy racers, once dismissed as impractical, had taught Mitchell that every ounce of drag mattered, that aerodynamic efficiency translated directly into performance, and that radical designs could succeed if the engineering was sound. He carried those lessons into the Spitfire, creating a fighter that remained competitive throughout the war and beyond. Later variants fought in Korea, flew reconnaissance missions into the 1950s, and set post-war speed records. The basic design, conceived by Mitchell in the mid-1930s, proved adaptable and enduring. Mitchell's approach, methodical and data-driven, became the foundation of modern aircraft design. Engineers no longer trusted intuition or tradition. They measured, calculated, and tested. Wind tunnels, stress analysis, and computational methods replaced guesswork. Mitchell had shown that aerodynamics was a science, not an art, and that disciplined application of physics could produce extraordinary results. His influence extended far beyond the Spitfire, shaping the development of jet fighters, commercial airliners, and spacecraft. In the decades following his death, Mitchell's reputation grew. Historians studying the Battle of Britain recognized that the Spitfire's performance had been critical to the RAF's victory. Without it, the Luftwaffe's Bf-109 would have dominated the skies, and Britain's fighter defenses might have collapsed. The Spitfire's speed, climb rate, and maneuverability gave RAF pilots a fighting chance, and in a battle as close as Britain's survival in 1940, a fighting chance was enough. Mitchell's personal sacrifice added poignancy to his legacy. He designed the Spitfire while dying, knowing he would never see it fulfill its potential. He worked through pain, pushing himself to complete the design, refining details even as his body failed. His dedication inspired those who worked with him, and his death at 42 robbed Britain of one of its greatest engineers. Yet his work endured. The Spitfire became the aircraft that defined British air power, a symbol of resilience, ingenuity, and the triumph of engineering over adversity. Sir Robert McLean, Supermarine's chairman, once said that Mitchell's greatest quality was his refusal to accept limitations. When told something was impossible, Mitchell calculated whether it was actually impossible or merely difficult. More often than not, it was merely difficult. The elliptical wing, considered too complex to manufacture, became one of the most efficient wing designs ever created. The thin wing, thought too weak to carry armament, proved strong enough through careful structural engineering. The high-speed monoplane, dismissed as impractical for military use, became the standard for all future fighters. Mitchell's legacy is not a monument, but a principle. That careful measurement, rigorous analysis, and disciplined engineering can solve problems that intuition and tradition cannot. He taught aviation that speed is not achieved by adding power, but by eliminating drag. That strength does not require heavy construction, but efficient distribution of stress. That innovation requires questioning assumptions, testing alternatives, and trusting data over opinion. These lessons, learned through years of designing racing seaplanes and refined in the crucible of war, remain the foundation of aerospace engineering. When the last Spitfire rolled off the production line in 1948, over 20,000 had been built, making it one of the most produced British aircraft in history. Variants served in dozens of air forces, fought on every front, and earned a reputation as one of the finest fighters ever created. Pilots loved the Spitfire for its handling, its responsiveness, and the confidence it inspired. Engineers respected it for its elegant design, its adaptability, and the brilliance of its conception. And historians recognized it as the aircraft that helped save Britain in its darkest hour. Reginald Joseph Mitchell never sought glory. He sought perfection. The Spitfire was as close as he came. It was not perfect, no aircraft ever is, but it was extraordinary. It combined speed, agility, firepower, and beauty in a way few aircraft have matched. Its elliptical wings, sleek fuselage, and graceful lines made it instantly recognizable. But beneath the beauty was precision engineering. Every component optimized, every curve calculated. Mitchell's genius lay not in creating something beautiful, but in making beauty and function inseparable. Mitchell died before the world knew his name, before the Spitfire proved itself in battle, before history recognized his contribution, but his work spoke for him. Every Spitfire that took to the skies carried his fingerprints, his calculations, his refusal to accept the limitations others imposed. The racing seaplanes they mocked became the foundation of the fighter that saved a nation. The monoplane they dismissed as impractical became the standard all others were measured against. And the quiet engineer from Stoke-on-Trent, who died at 42, became one of the most important figures in aviation history. His story is a reminder that the greatest achievements often come from those who question convention, trust their analysis, and refuse to accept that something cannot be done. Mitchell's Schneider racers proved that speed was achievable. His Spitfire proved that speed was practical, and his legacy proved that rigorous engineering, disciplined thought, and meticulous attention to detail can change the world. The racing plane they ridiculed became the savior of the skies, and the man they doubted became the engineer whose work defined an era.